Today we're going to look at how astronomers can find other planetary systems, that is, planets that are orbiting around stars other than the Sun. A lot of times we refer to these as extrasolar planets. Since 1995, we've found over 1,700 planets orbiting other stars. It's actually the numbers well over 3,000 if you count candidates that have not yet been confirmed. Basically, these discoveries sort of shake what we know, because we've always had this attitude that we're sort of the center of the universe, which of course was challenged during the Copernican Revolution when we realized that the planets do not orbit around the Earth. But it also gives us pause because we realize that here on Earth we might not be all that unique, and there might be many other solar systems out there in our universe that we haven't found yet. Basically, it gives us things to think about, like, how do we define a planet? We can't just think about planets that orbit the Sun. How big can an object be and still be considered a planet? Where's the line between a planet and a brown dwarf? When we find these planetary systems, will it help us test our nebular theory, or will it cause us to want to rethink things? It also is interesting to think about the fact that when we're looking for these extrasolar planets, we're actually looking in a region very close to us because of limitations of distance and what we're trying to find, which is very small. Most of the things that we've found so far are within a region of about 300 light years away from our Sun. What we found so far beyond our solar system is we found 1,781 total exoplanets, although there are nearly 5,000 candidates that haven't been confirmed yet. Stars that have planets is well over 1,000. We have found over 400 gas giants, over 1,000 hot Jupiters, and 84 terrestrial planets. What are the challenges to finding these extrasolar planets? Well, first of all, it's the scale and the distances that we have to deal with. Finding an Earth-like planet orbiting the nearest star is like looking from San Francisco for a pinhead orbiting 15 meters from a grapefruit in Washington, D.C. It's absurd, but it gives you a sense of what we're trying to do. Seeing a Jupiter-like planet is like seeing a marble 80 meters from the grapefruit-sized star. The other thing that's really hard to do in terms of finding the planets is the fact that when we're looking at those stars that the planets might be orbiting around, the brightness of the stars is so much greater than that of the planets, it's impossible or nearly impossible to actually directly observe them. So when we talk about the ways that astronomers can use to find the planets, they fall into two categories. They're either direct or indirect. A direct technique is basically when you have a picture or a spectra that actually itself gives direct evidence of the existence. For instance, we might find planets found when the light from a star is blocked out in an image would be a direct detection of a planet because we know exactly what's blocking that light. Much more common is the indirect measurements, where we're measuring the stars and how they move, and their motion is actually giving us a hint that there might be a planet orbiting around them. Mainly what we're looking at is what we call gravitational tugs caused by the orbiting planet. And we can measure this using either what we call the astrometric technique or the Doppler technique. So what is the gravitational tug? Well, when you think of a system of a planet and the star that it's orbiting around, there's a point in between them which we call the center of mass. I like to think of it this way. If you had two children on a seesaw, the center of mass is where the pivot point would be so that the two children could absolutely balance. When you have one object that's much bigger than the other, you probably know through practical experience that that pivot point has to be closer to the heavier person than towards the lighter person. And so when you're talking about a planet orbiting a star, the star is always much more massive. So the center of mass is very close to the star, if not even within the star itself. Well, the reason we bring this up is because when a planet is orbiting the star is also orbiting as well. they're actually both orbiting about this common point between them that we call the center of mass. And so what we're really looking at when we talk about gravitational tug is we're talking about the very small motion that the star goes through, because it's caused by the gravitational pull that the planet exerts on us. So we don't really have just a planet orbiting a central star, but we have a planet and a star orbiting a central point, which we call the center of mass. We never brought that up before because it was really no reason to, but now that we're talking about searching for other planets, we really need to be aware of that. So, the idea is that in any planetary system, all the objects are orbiting around the common center of mass. Because of that, the stars that we are able to see pretty readily can actually be observed to be going through some sort of circular motion or wobble. And it's that wobble that astronomers are looking for that help them detect that or infer that there might be a planet orbiting that star. Just to give you a sense, here's a big blown up picture of the motion of the sun over a period of a long time. Notice, however, the scale on here. It's very, very small. At first you think, oh wow, the sun is going all loop-de-loop, but notice that this is just a very small fraction of an arc second. So it's a very subtle motion, which gives you some appreciation of how hard it is to find these. So as we said earlier, there are two basic ways to see the effect of this gravitational tug. You can either do it through what we call astrometric measurements or Doppler measurements. Remember the Doppler effect that we talked about when we talked about light? We have to be aware of it and think about it once again. First of all, let's talk about the astrometric technique because it's a little more straightforward. Basically what you're doing here is you're using very precise measurement of stellar positions over time, because if you notice a very predictable movement over time, something that repeats itself in a very predictable way, you could say that it's going through its orbit in a certain amount of time, and from that you could say, well, that star is experiencing a gravitational tug, and then you might say that might be caused by a planet orbiting around it. We actually already use this to detect binary star systems. It might surprise you to know that many stars are actually part of a two-star system, which is called binary star systems. And in that case as well, they're both orbiting around a common center of mass. This is a very difficult thing to see, is the motion by the planets, because the motion of the star could be very subtle, as we saw in the last slide showing the motion of the sun. It's also going to depend on how close that star is to us. The closer the star is, the easier it will be for us to see the motion. As the star's distance from us increases, the motion that we're trying to see will become less and less noticeable. If the motion of the star is taking place over a very long period of time, this can also cause trouble. As you'll see in many of the graphs that we eventually show, we're looking at motions that take place over a period of days or maybe a month or two, nothing like years. That would take too long to measure at this point. This method is best used for studying massive planets orbiting nearby stars because of the limitations. We're going to stop here and then continue talking about the Doppler effect in the next video.